An in-silico analysis and narrative synopsis confirming the invalidity of ORP use in estimating aqueous H2 concentration. By Tyler W. LeBaron and Randy Sharp. The aim of the study is to conduct an in-silico analysis and provide a narrative synopsis confirming the invalidity of ORP use in estimating aqueous H2 concentration. Oxidation-reduction potential, ORP, is often used to characterize functional beverages, specifically alkaline ionized water and hydrogen water. Numerous health benefits including antioxidant effects have been attributed to a negative ORP value. However, a greater negative ORP value is often incorrectly interpreted to mean a greater degree of health benefits and/or a high concentration of H2. However, ORP is not specific to H2 gas but any redox-active molecules. Recent fatalities have occurred due to conflating a negative ORP with health benefits due to the use of toxic chemicals to induce a negative ORP. Additionally, when ORP meters are used to estimate H2 gas, the readings can be highly unreliable. For example, hydrogen meters use the Nernst equation to calculate the concentration of H2 based on the measured ORP value. Unfortunately, due to the fundamental limitations of the ORP meter, the calculated H2 value may be very inaccurate. Using the Nernst equation, we performed an in-silico analysis of the ORP as a function of pH, temperature, and H2 concentration. Our analysis shows that a 1-unit increase in pH, for example, 7 to 8, influences the ORP by as much as increasing the H2 concentration by 100 times, for example, 1 to 100 mg per liter. Similarly, at a saturated H2 concentration, 1.57 mg per liter, and pH 7, every delta T of 20 degrees C changes the ORP by approximately equal 30 meters V. This is comparable to changing the H2 concentration by a factor of 10, 0.1 mg per liter to 1 mg per liter. Moreover, to measure H2 within 0.1 mg per liter, ORP meters need to have an accuracy of about 0.8 mV. However, ORP meters have an error range of at least plus or minus 10 meters V, which corresponds to a potential error in measured H2 concentration of nearly 2 mg per liter, approximately equal 125% error. This analysis shows that pH, temperature, and intrinsic ORP errors can individually influence the ORP greater than the entire contribution of dissolved H2 within normally used ranges. Consequently, this can easily result in a water sample with a greater negative ORP than another despite having significantly less H2. Thus, it becomes impossible to consistently determine if one water sample has more H2 than another water sample. However, the analysis and calculations were performed only with the variables included in the equations, which can be considered a limitation of this study. Finally, we can only conclude, based on a negative ORP reading, that, excluding the possibility of other reductive redox couples, some level of dissolved H2 is present in the water. Accordingly, ORP and ORP-based H2 meters are not reliable for testing or comparing the concentration of H2 in water. Inherent fluctuations in the ORP meter, combined with the significant influence that even small deviations in pH and temperature have on the ORP, will always dominate the ORP measurement. you for watching this video. Please subscribe our channel for watch more scientific research videos.